there. Yes, you. I'm looking at you, just as you're looking at me. But does that mean that we're looking at each other right now? I don't know about you, but I would say no, not really. I can also say that I'm not affected by whatever you are feeling in this moment, simply because I can't see you. I would also guess that whatever emotion I display, you will recognize, but it won't affect you either. Seeing me on your computer screen is not the same as talking to me personally. Being able to understand another person's emotions, intentions, and expectations, and to also react to those, is easier the more you are socially involved in a situation. That's because our brain evolves in a socially rich and responsive environment in which we are constantly required to process faces and facial expressions that actually hold relevance to ourselves. That is the normal operating mode of face perception in the human brain. However, in conventional laboratory studies on face perception, a much more observational approach is taken, quite similar to seeing me on your computer screen right now. Face perception is usually investigated using planar, grayscale 2D images of faces that are presented on a computer monitor in a standardized size and at an undeniable distance created by the screen. But are the results obtained from these controlled conditions actually transferable to face perception in real life? We asked ourselves the same question. This is why we want to take a step towards bridging the gap between the laboratory and real life by introducing virtual reality to the lab. VR is technically capable of presenting 3D persons within an immersive scene in real-life size at personal distance to the participant. At the same time, high experimental control is preserved, and measuring electrophysiological data, for example via EEG, is possible at the same time as wearing a VR headset. In order to be able to compare our results obtained in VR with their laboratory counterparts, we presented pictures of persons and two control images to our participants in 2D on a PC monitor and also in 3D via VR headset. The pictures of 120 randomly selected persons were taken with our 3D 360 degrees camera. We then investigated the typically face-specific ERP component N170 as well as later components and compared the results between the two modalities. While the N170 managed to discriminate faces and controls in our laboratory condition, it failed to do so in VR, where no significant discrimination could be observed. However, when looking beyond the time frame of the N170 component, a different picture emerged. At a later time point, we find the same topographies for all stimulus types under laboratory conditions, while under realistic conditions the topographies differ markedly. Thus, distinct neural mechanisms for face, silhouette, and object perception are applied under realistic conditions, while the same object perception mechanism is used under laboratory conditions. What can we take from these results? The N170 component is face-sensitive, but only for faces on a computer screen, which makes it a domain-specific ERP component. As such, it has its value, since faces on screens are also part of our everyday life. However, encountering a realistic face requires more profound processing, as it is the normal operating mode of the brain, which is reflected by later components, as our results have shown. This cannot be observed in the conventional lab, but only under realistic conditions. Bringing VR into the lab thus takes us closer to uncovering what is really going on in the brain when we see other people. For real, not just on a screen.